In this video, we introduce our paper co-synthesis of histopathology nuclei image label pairs using a context-conditioned joint diffusion model. The limited availability of labeled training data has been a major bottleneck in learning-based nuclei analysis methods. To overcome, we propose using generative data augmentation to improve model performance, specifically focusing on generating realistic pathological textures, aligned image label pairs, and ensuring accurate instance separation. Previous methods, like Diffmix, have used random perturbations such as copy and paste to generate new images. However, these approaches do not consider the pathological context, which is crucial for generating realistic synthetic data. Other approach focused on generating cell layout labels, but failed to provide pixel-level semantic labels, making them less applicable for segmentation tasks, which is critical in histopathology. Our approach uses a joint diffusion model for co-synthesizing image label pairs, incorporating context conditions that allow for user controllability and generate realistic data. For instance, by using a nucleus centroid layout, we can spatially control the generated outputs. Furthermore, we incorporate text prompts to ensure the generated data aligns with specific pathological conditions such as organ and nuclei types. In our method, we augment the training data by generating synthetic image label pairs, using a joint diffusion process. The denoising network processes both image and label data simultaneously, ensuring their alignment and quality. Our joint diffusion process operates in both forward and reverse directions, modeling both continuous and categorical data. This process allows us to maintain high-quality alignment between the generated images and their corresponding labels. Now, let's take a look at the synthetic samples generated by our model. We evaluated our method on several data sets, including lizard, endonic, and panic. The samples show a high level of alignment with the real histopathology images, including realistic textures and well-separated nuclei. This demonstrates that our model effectively synthesizes data that is both realistic and useful for training downstream tasks. In terms of quantitative metrics, our model outperformed existing generative methods in generating realistic and useful data for downstream segmentation and classification tasks. Text conditions on organ types contribute to synthesizing realistic images from multi-organ datasets compared to SDM, which synthesizes images using semantic label conditions. For further validation, we conducted an expert analysis, where 5 pathologists evaluated both synthetic and real image label pairs. As shown in the graph on the left, the synthetic images received higher realism ratings than the real images, while the synthetic data received similar ratings to the real data, as shown in the graph on the right. We further analyzed the performance of our model in instance separation tasks, comparing it with Yu et al.'s method and a conventional algorithm. On all the datasets, our model outperformed others with a higher MDICE score, achieving values like 0.975 for on lizard and 0.963 for on endonic, demonstrating the efficiency of the nucleus centroid condition for instance separation. Finally, we assessed the downstream task performance in segmentation and classification. Our model not only improved segmentation results, but also boosted classification accuracy. For instance, in panic, our method achieved a DICE score of 0.824 and an accuracy of 0.736, outperforming both the baseline and SDM models. This result shows the effectiveness of our method in generating diverse label sets for different downstream tasks. Our model consistently outperformed SDM across multiple augmentation sets, achieving higher DICE scores as the number of augmentation sets increased. For classification tasks, our model demonstrated superior performance, achieving higher classification accuracy across multiple augmentation sets. This shows that our method not only improves segmentation results, but also significantly enhances classification performance by generating diverse and realistic label sets. In conclusion, we introduced a novel approach to co-synthesize image label pairs for histopathology nuclei images. We model the joint distribution of image, semantic label, and distance map using a single joint diffusion model. We introduced context conditioning methods, a point map and text prompt for precise controllable label synthesis process, and realistic synthesis of histopathology images. We use the synthesized distance mask to obtain instance label maps for downstream tasks such as nuclei instance segmentation. For future works, we plan to reduce the time cost for data synthesis and develop generative methods for creating realistic point layouts.